Welcome to Wildlife for Sleep, a place where ancient oceans breathe slowly, where shadows drift beneath the waves, and where stories are told, not to awaken the mind but to gently quiet it if these facts help you relax or slowly drift into sleep. Please like the video, subscribe to Wildlife for Sleep, and share your thoughts in the comments. Your support helps this channel continue creating peaceful, slow science-inspired sleep documentaries. Now settle into a comfortable position, let your breathing soften, and allow the surface world to fade away. Tonight we descend into the deepest waters of the sea. The ocean covers more than 70% of Earth's surface, yet most of it remains unexplored, unmapped, and largely unknown. Beneath the moving skin of waves and weather lies a vertical world, stacked in layers of temperature, pressure, and light. A world where sunlight fades within a few hundred meters, where cold becomes constant, and where pressure increases with every descending breath. This is the deep sea, and within this immense, three-dimensional environment lives one of the planet's most elusive large animals, the giant squid. For centuries, its existence was inferred rather than observed from fragments pulled up in fishing nets, from massive eyes preserved in museums, from circular scars found on the heads of deep-diving whales. These indirect signs hinted at encounters taking place far below human reach. Silent struggles unfolding in darkness. Only recently has modern technology allowed brief glimpses of the animal alive in its natural habitat, revealing not a monster, but a highly specialized deep-sea predator, perfectly adapted to life in cold, low-light environments. The giant squid is a pelagic cephalopod, meaning it lives suspended in open water rather than resting on the seafloor. It occupies primarily the mesopelagic and bathypelagic zones, typically between 300 and 1,000 meters deep, though individuals may travel far beyond these ranges. Here, light is scarce and temperatures hover near freezing, and food arrives unpredictably, drifting downward from surface ecosystems above. In such conditions, survival favors efficiency. The body is built for patience. Three hearts circulate copper-based blood through powerful mantle muscles and delicate gills. 8 arms and 2 specialized feeding tentacles carry rows of toothed suckers designed to secure slippery prey. A sharp beak, hidden at the center of this living net, processes captured animals with mechanical precision. But perhaps the most striking adaptation lies in its eyes. Each eye can reach extraordinary size, evolved to detect the faintest contrasts in near-total darkness. These organs are not designed for color or fine detail. They are tuned for motion, for silhouettes, for sudden changes in the dim glow produced by bioluminescent organisms drifting through the water column. This sensory system allows the squid to interpret a world built almost entirely from shadow. Life begins quietly. Eggs are released directly into open water, forming diffuse clouds that drift with currents. There is no parental care, no nesting site, no protection. Survival depends on numbers and probability. Only a small fraction of hatchlings will live long enough to reach juvenile stages. Those that do begin life as tiny, nearly transparent larvae, carried passively through upper and mid-water layers. Over time, they descend gradually into deeper zones, growing larger, strengthening their mantle muscles, extending their arms, and refining their hunting coordination. Development is continuous. There is no abrupt transition from youth to adulthood. Only a steady accumulation of mass, experience, and physiological capability. Movement is achieved primarily through jet propulsion. Water is drawn into the mantle cavity and expelled forcefully through a flexible siphon, generating thrust. This allows rapid bursts of speed when hunting or escaping threats. Between these bursts, the squid relies on slow fin movements and passive drifting, conserving energy in an environment where every calorie matters. Feeding follows a pattern of long waiting periods interrupted by brief moments of decisive action. The squid typically positions itself beneath potential prey, remaining motionless until fish or other mid-water animals pass within reach. The two feeding tentacles then extend in a fraction of a second, securing the target and drawing it inward toward the arms and beak. This strategy minimizes energy expenditure while maximizing capture success. The giant squid does not roam constantly. Instead, it occupies shifting volumes of water, rising and sinking with daily vertical migrations of prey, traveling great distances on slow ocean currents, inhabiting a moving habitat defined by temperature gradients and food availability rather than physical landmarks. Throughout its life, the squid remains solitary. There are no schools, no permanent social groups. Encounters with others of its kind are rare and brief, likely limited to mating events later in adulthood. Much of what scientists know comes from indirect evidence: stranded individuals, remotely operated vehicles, and deep-sea cameras deployed for only hours at a time in an ocean that never truly rests. Eventually, after years of growth, feeding, and migration, the adult squid reaches reproductive maturity. Spawning marks the final major phase of its life cycle. After reproduction, the body weakens, energy reserves decline, and death follows not as an isolated event, but as part of a broader system. The remains sink. They become nourishment for deep-sea scavengers and microorganisms. Carbon and nutrients are returned to the ocean interior, and the cycle continues from drifting egg to apex mid-water predator, from solitary hunter to sinking source of life. The giant squid exists as both consumer and contributor within Earth's largest ecosystem. Its story is not one of dominance. It is one of adaptation, of efficiency shaped by pressure, of perception forged in darkness, and of life sustained in one of the most challenging environments on our planet. Reproduction in the deep pelagic ocean is not organized around nests, reefs, or sheltered nurseries. It takes place in open water, in moving darkness, guided not by geography, but by currents at maturity. The giant squid releases vast numbers of eggs directly into the surrounding sea. There is no parental care and no fixed spawning ground. Instead, fertilized eggs disperse as diffuse clouds, suspended in the water column and carried by large-scale ocean circulation. Each egg is small, fragile, and nearly transparent. Yet inside every one lies a complete biological blueprint. Instructions for building enormous eyes, powerful mantle muscles, specialized tentacles, and a nervous system capable of coordinating rapid predatory strikes in near total darkness. Most of these eggs will never hatch. Some are consumed almost immediately by plankton-feeding organisms. Others fail during early development. This is not an exception in the deep sea, it is the rule. Survival depends on numbers. Evolution has favored quantity over protection, ensuring that at least a small fraction of offspring will persist. Within the surviving eggs, embryonic development proceeds slowly in cold water. Cells divide, tissues differentiate, primitive organs take shape. Tiny hearts begin to pulse for the first time, circulating copper-based blood through microscopic vessels. All of this occurs unseen, under pressures that would crush surface-dwelling animals in seconds. When hatching finally occurs, it is subtle. The egg membrane weakens and a larva emerges. At this stage, the young squid, called a paralarva, is extraordinarily small. Its body is almost glass-like. Arms are short. Muscles are weak. Vision is limited. Propulsion is gentle and inefficient. Rather than actively swimming, it drifts, moving largely at the mercy of surrounding currents. This early life unfolds higher in the water column than adulthood, within pelagic zones populated by plankton, gelatinous organisms, and larval fish. Here, sunlight is faint but still present, filtering down as a muted blue glow. Food consists of microscopic crustaceans and other drifting life, captured with undeveloped arms and simple grasping motions. Predation pressure is intense. Everything feeds on small, drifting organisms. The young squid survives primarily through invisibility. Its transparent tissues scatter light, reducing contrast against the surrounding water. Movement is minimal. Metabolism is tuned for efficiency. Remaining unnoticed becomes its first and most important defense. Growth during this phase is rapid. Cells multiply. Muscle fibers thicken. Neural pathways expand. Chromatophores, pigment-containing cells that will later enable camouflage, begin forming beneath the skin. The eyes enlarge steadily, preparing for a future spent interpreting shadows rather than color. As weeks become months, the juvenile begins a gradual descent. This is not a single migration but a continuous process, driven by development and changing physiological tolerance. With increasing size comes the ability to withstand greater pressure and colder temperatures. The squid slowly transitions from brighter upper waters into the mesopelagic twilight zone, where light fades dramatically and prey communities shift. Internally, major systems mature in parallel. Three hearts coordinate circulation. Gills become more efficient at extracting oxygen from cold, low-oxygen water. The mantle strengthens, allowing controlled jet propulsion. The beginnings of two specialized feeding tentacles differentiate from the 8 arms, setting the foundation for future hunting behavior. Throughout this period, mortality remains high. Encounters with predators are frequent. Many juveniles are lost. Those that survive do so through a combination of rapid growth, passive drifting, and increasingly refined sensory awareness. There is no learning from parents, no social structure, no guidance beyond instinct. Every improvement emerges from direct interaction with the environment. By the time the young squid settles deeper into the twilight zone, it no longer resembles the fragile larva that once floated near the surface. Its body now has substance. Its arms show strength. Its visual system is becoming highly sensitive to motion and contrast. It has crossed a biological threshold. From this point forward, it is no longer merely drifting through ecosystems. It is entering the role of an active participant in them. The early pelagic nursery fades behind it. Colder layers receive it, and the long transformation from vulnerable hatchling to solitary deep-sea hunter continues. Juvenile life in the open ocean is defined by motion, not purposeful travel, but continuous displacement driven by currents, density gradients, and daily vertical migrations of surrounding organisms. At this stage, the young giant squid occupies the mesopelagic zone, a region often called the twilight layer, where sunlight fades rapidly and the environment becomes dominated by shadow and bioluminescence. There are no physical boundaries here, no reefs, no seafloor, no surface, only water extending in every direction. And within this three-dimensional space, survival depends on remaining difficult to detect. The juvenile squid still retains partial transparency. Light passes through much of its tissue, reducing contrast against the surrounding water. This transparency, combined with minimal movement, provides critical camouflage during a phase when strength alone is not yet sufficient for defense. Most motion is passive. The squid drifts with prevailing currents, making only small adjustments using its developing fins. Jet propulsion is used sparingly, reserved for short corrections in position or sudden escapes. Energy conservation dominates behavior. Every contraction of the mantle must be justified by nutritional gain or immediate survival. Feeding remains opportunistic. The juvenile captures small crustaceans, larval fish, and other drifting organisms. Arms extend cautiously. Suckers grip soft bodies. Prey is drawn inward and processed by the beak. Each successful feeding event contributes directly to growth, reinforcing muscle fibers, expanding neural networks, and supporting the continued enlargement of the eyes. Growth during this period is steady but variable. Food availability fluctuates with plankton blooms, current patterns, and seasonal productivity at the surface. During productive periods, development accelerates. During scarcity, metabolism slows and movement becomes minimal. The squid adapts by alternating between brief feeding windows and extended fasting. Daily vertical migration becomes part of its routine. At night, when many prey species rise toward shallower layers, the squid ascends slightly to follow them. During daylight hours, it sinks back into deeper, darker water where visual predators are less effective. This rhythm repeats continuously, creating a slow oscillation through stacked ecological layers. Sensory systems mature rapidly. The eyes grow larger and more sensitive, improving the ability to detect motion against dim background light. Pressure-sensitive tissues along the body register disturbances in surrounding water. Staticists provide orientation, helping the squid maintain balance in an environment without visual reference points. Together, these systems allow the juvenile to interpret a world built almost entirely from gradients. Gradients of light, gradients of temperature, gradients of pressure. Predation risk remains high. Midwater fishes, gelatinous predators, and larger cephalopods patrol these depths. Encounters are frequent, and escape often depends on early detection rather than speed. When threatened, the squid initiates brief jet bursts, rapidly increasing distance before settling again into passive drift. Small scars begin to accumulate, minor abrasions along arms, subtle marks on the mantle. Each represents a close encounter that did not become fatal. Over time, these experiences refine behavior. Reaction thresholds adjust. Escape responses become more precise. The squid learns when to flee and when stillness provides better protection. Physiologically, the transformation continues. The mantle thickens, fins broaden. The two feeding tentacles elongate relative to the arms, preparing for future high-speed strikes. Internally, the three-heart circulatory system becomes more powerful, supporting increasing body mass and sustained activity in cold, low-oxygen water. Transparency slowly gives way to opacity. Chromatophores multiply beneath the skin, granting the squid increasing control over its appearance. While still subtle at this stage, these pigment cells begin to provide dynamic camouflage, allowing the body to darken or pale in response to ambient conditions. The juvenile now occupies deeper layers more consistently. It spends less time near residual surface light and more time in the darker midwater, where prey sizes increase and competition shifts. With depth comes greater pressure, but also reduced visual exposure to surface predators. This marks an important transition. The squid is no longer merely surviving its early vulnerability. It is entering a phase of active development toward predatory capability. Drifting gradually becomes directed positioning. Passive existence begins to give way to intentional hunting. The transparent phantom is fading, and a structured hunter is beginning to emerge. The transition from drifting juvenile to active predator does not happen suddenly. It unfolds gradually, measured in millimeters of muscle, in strengthening nerve pathways, in the quiet accumulation of successful hunts. During this phase, the young giant squid begins to display the defining characteristics of adulthood. The mantle thickens first. Layer by layer, circular muscle fibers increase in density, transforming the mantle into a powerful biological engine. Each contraction becomes more efficient. Each jet of expelled water produces greater thrust. Along the mantle's edges, the fins widen and stiffen, improving stability and allowing controlled hovering in slow-moving currents. These changes mark a shift in mobility. The squid is no longer primarily a passenger of ocean circulation. It can now actively position itself within the water column. But the most visible transformation occurs in the arms and tentacles. The 8 arms grow longer and more muscular, their internal support structures strengthening to withstand greater force. Rows of suckers develop sharper rims and more pronounced internal teeth, improving grip on slippery prey. At the same time, the 2 specialized feeding tentacles extend far beyond the arms, becoming elastic, high-speed capture tools capable of rapid deployment. These tentacles are usually held tightly coiled. They remain hidden most of the time. Stored potential energy waiting for release. Their function is precise and brief, designed for moments that last less than a second. Hunting behavior evolves alongside this anatomy. Rather than feeding opportunistically on whatever drifts nearby, the squid now begins to select targets. It positions itself below schools of fish or clusters of mid-water organisms, remaining motionless while monitoring movement patterns through vision and pressure-sensitive tissues. This strategy minimizes energy expenditure. Instead of pursuing prey, the squid allows prey to approach. When a target crosses an invisible threshold of distance and alignment, the feeding tentacles extend explosively. Contact is immediate. Suckers engage. The captured animal is drawn inward toward the arms, which close to form a living enclosure. The beak then processes the prey with mechanical efficiency. Each successful strike reinforces coordination between sensory input and motor response. Neural pathways linking eyes, mantle, and tentacles become increasingly refined. Reaction times shorten. Accuracy improves. Missed strikes become less frequent as the squid learns the effective reach of its tentacles and the escape behaviors of different prey species. Internally, the circulatory system adapts to rising metabolic demands. 3 hearts maintain continuous flow of oxygenated, copper-rich blood through expanding tissues. Gills increase their extraction efficiency in cold, low-oxygen water. Digestive processes accelerate following feeding events, rapidly converting consumed biomass into usable energy for growth and maintenance. Chromatophores multiply beneath the skin. These pigment cells now provide dynamic camouflage, allowing the squid to adjust its appearance in response to ambient light levels. Darkening reduces silhouette visibility from below. Pale tones blend with faint background glow. This adaptive coloration enhances both hunting success and predator avoidance. Scars begin to appear more frequently. Minor abrasions on arms, small marks along the mantle. Each reflects close encounters with prey, competitors, or predators. Over time, these experiences refine behavior. The squid becomes more selective in its strikes and more conservative in its use of jet propulsion, conserving energy for moments when movement truly matters. Feeding patterns stabilize. Periods of active hunting alternate with long intervals of drifting and digestion. During times of prey abundance, growth accelerates. During scarcity, metabolism slows, and the squid relies on stored reserves. This ability to tolerate fasting becomes essential in an environment where food availability is unpredictable. With increasing size comes access to deeper layers. The squid now spends more time in colder zones where larger prey species reside. Pressure increases. Light diminishes further. But physiological tolerance keeps pace with environmental change, allowing continued expansion into bathypelagic depths. This stage represents a critical turning point. The squid is no longer defined by vulnerability. It is now defined by capability. Arms possess strength. Tentacles possess reach. Vision possesses range. Movement possesses purpose. The drifting youth has become a structured hunter, integrated fully into the mid-water food web, converting dispersed life into organized form through precision and restraint. The foundations of adulthood are now firmly in place, and with them comes a new level of interaction with the deep sea ecosystem. In the deep ocean, vision is not about color, it is about contrast. It is about detecting movement where almost no light exists. And for the giant squid, sight becomes one of its most powerful tools for survival. As the squid continues its transition into full predatory capability, its eyes undergo remarkable development. Each eye grows to extraordinary proportions, becoming among the largest visual organs in the animal kingdom. These massive structures are not designed for sharp detail or vibrant hues. Instead, they are optimized to gather the faintest available light and transform it into usable information. Inside each eye, a large lens focuses dim illumination onto a retina dominated by rod cells. These photoreceptors are highly sensitive to low light levels, allowing the squid to detect silhouettes, motion, and sudden changes in brightness. Color perception is minimal. What matters here is whether something moves and how fast. Down in the mesopelagic and bathypelagic zones, sunlight has nearly vanished. What remains comes from bioluminescence. Countless organisms produce their own light, tiny flashes from startled plankton, steady glows from gelatinous animals, brief pulses from fish attempting to confuse predators. To many creatures, this luminous noise is disorienting. To the squid, it is a map. Every sparkle outlines movement. Every glowing cloud reveals disturbance. When a large animal passes through dense plankton, it often triggers cascading waves of bioluminescence. For the squid, these glowing halos briefly trace the shapes of otherwise invisible bodies. Prey becomes outlined in light. Potential predators announce themselves in expanding rings of illumination. The squid learns to interpret these patterns instinctively. A slow-moving glow suggests drifting organisms. A sudden flare indicates rapid motion. A broad, expanding shimmer may signal something far larger. Vision becomes predictive. The squid does not simply react to what it sees. It anticipates trajectories. It estimates where prey will be moments later. It positions itself accordingly, hovering beneath moving targets, aligning its body with faint current flows, minimizing effort while maximizing opportunity. This ability transforms hunting strategy. Rather than chasing prey across open water, the squid adopts an ambush-based approach. It waits motionless in shadow, using its large eyes to monitor passing silhouettes above. Only when alignment and distance reach precise thresholds do the feeding tentacles deploy. This reduces energy expenditure and increases capture success. Visual input is tightly integrated with motor control. Neural pathways link the eyes directly to mantle muscles and tentacle deployment. Sensory information flows rapidly into action, allowing strikes to occur in fractions of a second. There is no hesitation, no conscious decision, only a seamless conversion of perception into movement. At the same time, vision supports predator avoidance. Large disturbances in the surrounding water column produce characteristic light patterns. The squid recognizes these instantly, initiating controlled jet propulsion away from danger before direct contact occurs. Often, escape begins before a threat becomes fully visible, guided by indirect visual cues amplified by bioluminescent response. With increasing size, visual range expands. Larger eyes collect more photons, extending detection distances. What once appeared as vague shadows now resolves into structured motion. Schools of fish become coherent forms, individual prey items separate from background noise. The squid gains the ability to hunt effectively in deeper, darker layers where competition is reduced but prey is larger. Internally, the brain adapts to this growing sensory load. Visual processing regions expand. Coordination between eyes, statocysts, and pressure-sensitive tissues becomes more refined. Orientation improves in a world without fixed reference points. The squid develops a continuous awareness of its position relative to moving bodies and drifting particles. Its environment becomes a dynamic field of gradients, brightness gradients, pressure gradients, motion gradients. And within this field, the squid learns to navigate with precision. It does not recognize landscapes. It does not perceive scenery. It experiences space as patterns of change. Light becomes geometry. Shadow becomes information. Movement becomes opportunity. Through this sensory specialization, the giant squid establishes itself as an efficient mid-water predator, capable of operating in conditions that would render most visual systems useless. Above, sunlight still defines day and night. Below, vision is forged from fragments of glow and absence. And here, in this layered darkness, the squid carries its own quiet observatory, two enormous eyes, continuously scanning a world built almost entirely from shadow. Active predation begins quietly. There is no dramatic acceleration into pursuit, no prolonged chase through open water. Instead, the giant squid approaches hunting as a problem of positioning, timing, and efficiency. The squid typically places itself beneath drifting prey layers, hovering with minimal fin movement while maintaining precise orientation using statistics and pressure-sensitive skin. Its mantle remains relaxed. Heart circulates steadily. Oxygen exchange through the gills continues at a low, stable rate. This is a waiting posture, energy conserved as sensory systems fully engaged. Prey is detected first as disturbance, subtle changes in surrounding pressure fields, faint silhouettes moving across dim background light, or brief flashes of bioluminescence triggered by passing bodies. Visual input is combined with mechanorception to establish distance, speed, and trajectory. The squid does not pursue immediately. It allows prey to approach. Only when alignment reaches an optimal configuration, when relative motion slows and distance falls within tentacle range, does the attack begin. The feeding tentacles deploy in a fraction of a second. They extend rapidly from their coiled resting position, driven by stored elastic energy and coordinated muscle contraction. At full extension, they reach far beyond the 8 arms, delivering sucker-lined clubs directly onto the target. Contact is immediate. Adhesion occurs through suction and tooth sucker rims, securing slippery tissue before the prey can react. The tentacles retract just as quickly, drawing the captured organism inward. The arms close around it, forming a temporary enclosure that guides the prey toward the beak. The beak, composed of dense chitin, delivers a decisive bite, fragmenting soft tissue and initiating digestion. Nutrients enter circulation within minutes, transported by copper-rich blood to muscles and neural tissue. The entire sequence, from detection to ingestion, often lasts only seconds. Then the squid returns to stillness. There is no lingering at the capture site. Chromatophores adjust skin tone to reduce contrast. Fins resume gentle stabilization. The animal drifts back into shadow, minimizing visibility while digestion proceeds. With repetition, this process becomes increasingly refined. Strike accuracy improves. Reaction time shortens. Approach angles become more consistent. Neural pathways linking vision, mantle contraction, and tentacle deployment strengthen with every successful capture. The squid develops an internal model of prey behavior, learning which species scatter upward, which dive, and which hesitate briefly before attempting escape. This predictive capacity reduces wasted effort. Jet propulsion is used selectively. Short bursts reposition the squid beneath prey layers or create rapid separation following a strike. Prolonged swimming is avoided. Instead, the squid relies on brief impulses of thrust followed by extended drifting, maintaining a favorable energy balance in an environment where food availability is unpredictable. Feeding patterns settle into cycles. Periods of active hunting alternate with long intervals of reduced movement and digestion. During times of prey abundance, growth accelerates. During scarcity, metabolic rate declines and stored reserves sustain basic function. This physiological flexibility allows survival across fluctuating resource conditions. Not every hunt succeeds. Some prey evade capture. Others break free from tentacle grip. These failures contribute to learning. The squid adjusts strike distance, modifies timing, and becomes more selective in target choice. Over time, unsuccessful attempts become less frequent. Predator avoidance is integrated into hunting behavior. Large disturbances in surrounding water, detected visually or mechanically, can interrupt a feeding attempt. In such cases, the squid abandons pursuit and initiates rapid jet propulsion away from the threat, often before direct contact becomes possible. Escape is prioritized over acquisition. Minor injuries accumulate during this stage of life. Small abrasions on arms, occasional marks on the mantle. Each reflects close encounters with prey or competitors. These experiences further refine behavior, reinforcing caution and improving situational awareness. Through repeated cycles of wading, striking, feeding, and drifting, the squid fully assumes its role as a mid-water predator. Energy is converted into structure. Structure supports motion. Motion enables further acquisition. This feedback loop drives continued growth and maturation. The first hunt is not a singular event. It is the beginning of a lifetime pattern, an ongoing sequence of precise actions embedded within long periods of stillness, sustained by sensory integration and muscular efficiency. Here, in cold, layered water far from surface light, predation becomes a quiet exchange between shadow and substance, a conversion of drifting life into organized form, a process repeated thousands of times across years of solitary existence. Locomotion in the deep pelagic ocean is governed by efficiency. There are no solid surfaces to push against, no reefs to shelter behind, no bottom to rest upon. Movement must be generated entirely from within the body and transmitted through water that resists every acceleration for the giant squid. This challenge is solved through a combination of muscular hydraulics, flexible anatomy, and careful energy management. At the center of its mobility lies the mantle. This thick, muscular chamber surrounds the squid's internal organs and functions as both engine and pump. During inhalation, the mantle relaxes and expands, drawing water into the mantle cavity. During exhalation, circular muscles contract, forcing that water outward through a narrow, adjustable funnel known as the siphon. This expelled jet produces thrust. The process is mechanically simple, yet biologically refined. The siphon can rotate, allowing thrust to be redirected in multiple directions. By altering the angle of water expulsion, the squid can move forward, backward, upward, or downward with precise control. This flexibility enables rapid reorientation during hunts and immediate retreat during predator encounters. Jet propulsion is not used continuously. Sustained high-speed swimming would consume energy too rapidly in an environment where food arrives unpredictably. Instead, the squid alternates between brief bursts of thrust and long periods of passive drifting. Between jets, movement is maintained primarily by the lateral fins. These fins extend along the mantle's sides and generate gentle lift and stabilization. Their slow, undulating motions allow the squid to hover in place, ascend gradually, or sink into deeper layers with minimal effort. This mode of travel is quiet and economical, producing little disturbance in surrounding water. Together, jet propulsion and fin-based cruising form a dual system: short, powerful accelerations, followed by extended stillness. This pattern dominates the squid's daily existence. During hunting, jet propulsion serves to refine positioning. Small corrective bursts place the squid beneath prey layers or align its body with drifting schools. Following successful strikes, brief jets may carry it back into deeper shadow while digestion begins. During predator encounters, the same system becomes a means of escape. A sudden mantle contraction produces rapid backward motion. Fins flatten against the body to reduce drag. The squid accelerates sharply, leaving behind turbulent water that may briefly glow with bioluminescent response from disturbed plankton. Within seconds, distance is created. Confusion follows. The squid vanishes into layered darkness. These escape responses are metabolically expensive. They cannot be sustained. But they do not need to be. In the deep sea, creating even a short separation often determines survival. Internally, propulsion is tightly integrated with respiration. Water drawn into the mantle delivers oxygen across the gills. Expelled water removes carbon dioxide and metabolic heat. Every jet therefore serves dual purposes: movement and gas exchange. During intense activity, circulation increases immediately. The three hearts elevate flow rates, ensuring that oxygen reaches working muscles and neural tissues. As the squid grows, the mantle thickens and propulsion efficiency improves. Larger individuals can generate stronger thrust while maintaining control over direction. At the same time, experience refines behavioral use of movement. The squid learns when acceleration is necessary and when remaining motionless offers better protection. This restraint is critical. Most of the squid's life is spent hovering, drifting, or slowly cruising. Long intervals of inactivity conserve energy and reduce detection risk. Only when prey approaches or danger becomes imminent does rapid movement occur. On larger spatial scales, locomotion is supplemented by ocean circulation. The squid becomes a passive traveler on deep currents, moving horizontally across vast distances without active effort. Vertical movements, daily ascents and descents following prey migrations, are achieved through a combination of fin motion, buoyancy adjustment, and occasional jet bursts. There are no permanent territories, no fixed routes. The habitat itself is in constant motion. The squid exists within shifting volumes of water defined by temperature, density, and food availability. Its movement patterns reflect this dynamic environment, balancing active control with passive transport. In this way, propulsion is not merely a means of travel. It is a strategy for inhabiting a world without boundaries, a method for conserving energy in scarcity, a mechanism for sudden response in crisis, and a bridge between stillness and action in the vast three-dimensional ocean. Here, in cold darkness far below surface waves, movement becomes measured and intentional, each jet a calculated expense, each pause an investment in survival. In the deep ocean, communication does not rely on sound, and it rarely relies on sight in the way surface animals understand it. Instead, information is exchanged through contrast, texture, and subtle changes in brightness, carried across short distances in water that absorbs light almost completely. For the giant squid, the skin itself becomes an active sensory and signaling surface. Beneath the outer layer of the mantle and arms lies a dense network of chromatophores, specialized pigment containing cells connected directly to the nervous system. Each chromatophore consists of a tiny elastic sac filled with pigment surrounded by radial muscles. When these muscles contract, the sac expands, darkening that patch of skin. When the muscles relax, the pigment retracts, allowing the area to become pale again. This process occurs in milliseconds. The result is dynamic camouflage. Unlike animals that change color slowly, the giant squid can alter its appearance almost instantly, producing shifting patterns of light and dark across its body. These changes are not decorative. They are functional responses to environmental conditions, emotional state, and immediate behavioral needs. In deep water, where color perception is minimal, what matters is brightness. The squid adjusts its skin to match surrounding darkness, reducing its silhouette when viewed from below. Against faint background glow, it may pale slightly. In deeper layers, it darkens almost completely, becoming a moving absence rather than a visible form. This is countershading in 3 dimensions. Not a fixed pattern, but a continuously updated response to ambient light. Chromatophores also play a role in hunting. As the squid hovers beneath prey, subtle darkening helps break up its outline, preventing fish from detecting its approach. During the final moments before a strike, the body often becomes uniformly dark, minimizing reflective surfaces that could betray movement. Immediately after capture, chromatophores may briefly flare, then settle again as the squid returns to stillness. These flashes are not communication with others. They are physiological echoes, reflections of neural activity and muscle engagement. The giant squid is solitary. It does not maintain social bonds. Encounters with others of its kind are rare and likely limited to reproductive events later in life. As a result, chromatophore displays are not used for group coordination or courtship rituals in the way they are among shallow water cephalopods. Instead, skin patterning serves three primary functions: camouflage, predator avoidance, and internal state regulation. During moments of stress, such as sudden disturbances in surrounding water, the chromatophores respond immediately. The body darkens sharply as the squid prepares for jet propulsion. This rapid shift may reduce visibility during escape, blending the animal into deeper shadow as it accelerates away. At rest, patterns become more muted. The mantle adopts a low-contrast tone that mirrors surrounding water conditions. Arms hang loosely. Fins stabilize gently. The squid becomes visually quiet, merging with the layered darkness around it. Internally, chromatophore control is tightly integrated with the nervous system. Visual input, pressure sensing, and motor planning converge in neural centers that coordinate both movement and skin response. A detected threat triggers mantle contraction and chromatophore expansion simultaneously. A successful strike is followed by coordinated relaxation across multiple systems. Skin becomes part of behavior. It is not merely protective covering. It is an extension of perception and action. On microscopic scales, additional reflective cells and structural elements modify how light interacts with tissue, further reducing visibility. Together with transparency in younger stages and increasing opacity in adults, these features allow the squid to adapt its appearance throughout life. As size increases and the animal occupies deeper layers, chromatophore patterns become darker and more uniform. The need for rapid visual blending intensifies in regions where bioluminescent flashes can suddenly reveal moving bodies. In these environments, the squid's ability to vanish into darkness becomes as important as its ability to strike. There is no sound to announce its presence, no wake to mark its passage for long, only brief disturbances in drifting particles, only transient glows from startled plankton, and then nothing. The language of color here is quiet. It is spoken in gradients. It is written in shadow, and it allows a large, muscular predator to exist in open water without constantly advertising itself to everything nearby. Through this silent dialogue with light and darkness, the giant squid maintains its place within the midwater ecosystem, present, active, and yet remarkably difficult to detect. Life in the midwater ocean follows a rhythm that is invisible from the surface. a slow, vertical pulse driven by light, temperature, and the movement of prey. For the giant squid, this rhythm defines nearly every aspect of daily existence. The squid inhabits primarily the mesopelagic region, often called the twilight zone, a vast layer of ocean extending roughly from 200 to 1,000 meters below the surface. Here, sunlight fades rapidly with depth, creating a world of perpetual dusk. There is no true day or night in the way land animals experience it. Instead, brightness shifts subtly, and these changes ripple through the entire food web. Each cycle begins with ascent. As surface light weakens in the evening, countless small organisms migrate upward. Zooplankton rise first. Small fishes follow. Larger predators track these movements from below. The squid senses this change through faint increases in bioluminescent activity and subtle pressure disturbances carried by moving bodies. It responds by rising slowly, not with continuous propulsion, but through gentle fin motion and controlled buoyancy, allowing surrounding currents to assist the climb. This ascent is measured, economical, and deliberate. The squid positions itself beneath emerging prey layers, maintaining a hovering posture that maximizes detection while minimizing movement. Here, feeding opportunities increase and hunting becomes more frequent. During these active periods, the squid alternates between brief strikes and long pauses. It waits, then deploys its feeding tentacles, then drifts again. Each capture is followed by a return to stillness as digestion begins. Energy gained from prey supports ongoing metabolism, tissue repair, and continued growth. There is no frenzy. Even during abundance, the squid maintains restraint, avoiding unnecessary motion. As ambient light increases with the approach of daytime, prey species begin their descent. The squid follows. It sinks gradually into deeper, darker layers, returning to regions where visual detection by surface-oriented predators is reduced. Here, activity levels decrease. Movement becomes minimal. Feeding slows or stops entirely. Metabolic rate drops and the squid enters extended periods of low energy hovering. These quieter hours are not empty. They are essential. This is when digestion completes, when damaged tissues are repaired, when neural systems consolidate the sensory information gathered during hunting. The squid remains alert, but it conserves energy, allowing the ocean itself to carry it gently through layered water masses. Falling organic particles, often called marine snow, continue to drift downward from surface ecosystems. Tiny fragments of life pass by constantly, reminders that distant productivity supports deep-sea communities. While these particles are not a primary food source for the squid, they sustain the broader system on which its prey depends. Over weeks and months, this daily vertical migration repeats thousands of times. The distances traveled in each cycle may be modest, but together they define the squid's spatial existence. It does not hold territory. It does not return to specific locations. Instead, It occupies moving volumes of water shaped by temperature gradients, oxygen levels, and prey density. Horizontally, the squid is carried by deep currents. These slow, persistent flows transport it across kilometers without active effort. Over years, an individual may traverse vast regions of ocean basin, never recognizing boundaries, never encountering familiar landmarks. The habitat itself is dynamic, continuously reshaped by planetary circulation. Feeding success varies. Some nights provide abundant prey, others offer little. The squid adapts by modulating activity levels. During scarcity, it reduces movement and relies on stored reserves. During abundance, it feeds more frequently but still avoids wasteful exertion. This flexibility is central to survival in an environment where resource availability is unpredictable. Throughout this routine, solitude remains constant. There are no companions during migrations, no coordinated group movements. Encounters with other large animals are rare and brief. Most interactions occur indirectly, mediated through shared prey fields rather than direct contact. Physiologically, the squid systems remain finely balanced. 3 hearts maintain circulation. Gills extract oxygen from cold, low-oxygen water. Muscles alternate between extended rest and sudden activation. Chromatophores adjust skin brightness in response to changing light conditions. Every component works together to support a lifestyle built on patience punctuated by precision. This is daily life in the twilight zone, a repeating cycle of ascent and descent, of waiting and striking, of drifting and digesting. A quiet routine sustained over years, far from surface storms and coastal noise. Here, existence is shaped not by landscapes but by layers, not by landmarks but by gradients. And within this moving architecture of darkness, the giant squid continues its solitary journey, converting scattered life into motion and motion into survival. In the open mid-water ocean, few encounters carry greater consequence than those between the giant squid and the sperm whale. These meetings are rarely witnessed directly. They take place far below sunlight, beyond the reach of most cameras, in water compressed by immense pressure. What scientists know comes from indirect evidence: circular scars on whale skin, fragments of squid recovered from stomachs, and rare deep-sea recordings that capture only brief moments of approach or retreat. Yet even these fragments tell a consistent story. Here, predator and prey meet in darkness. The sperm whale is a specialist diver, capable of descending more than a kilometer beneath the surface in search of large cephalopods. Its massive body carries reserves of oxygen that support long foraging dives. Instead of relying primarily on vision, the whale navigates using echolocation, emitting powerful clicks and interpreting returning echoes to locate prey in pitch-black water. For the squid, this creates a new kind of threat. Vision and camouflage, so effective against most mid-water predators, offer limited protection against acoustic detection. A descending whale announces its presence through pressure waves and distant sound, signals that propagate efficiently through water. The squid often senses the approach before it sees anything. Subtle vibrations pass through surrounding fluid. Background bioluminescence shifts as smaller organisms scatter. The water itself seems to tense. In response, the squid alters posture immediately. Chromatophores darken the mantle. Fins flatten. The body angles downward, preparing for rapid jet propulsion if needed. Escape becomes the priority. But speed alone cannot guarantee survival against an animal many times larger. The squid relies on unpredictability. Short, powerful bursts of jet propulsion carry it sideways or downward into deeper layers. Direction changes occur rapidly as the siphon pivots, redirecting thrust in sharp angles. The goal is not sustained flight but disruption, creating confusion in acoustic tracking and forcing the whale to continually recalculate position. Sometimes this works. Distance opens. The whale abandons pursuit. The squid disappears into layered darkness. But not every encounter ends this way. When contact occurs, the interaction becomes physical. The squid deploys its arms and feeding tentacles defensively, attempting to attach to the whale's head or flanks. Suckers with hardened rims leave circular impressions in the whale's skin, marks that may persist for years. These scars, often observed on adult whales, serve as lasting records of close combat in the deep. The beak may be used as well, targeting soft tissue where possible. These actions are not attempts to defeat the whale. They are attempts to create space, to disrupt orientation, to force release. For the whale, such encounters are part of a broader foraging strategy. Even when resistance is strong, the whale's size and strength usually prevail. Captured squid are brought to the surface or consumed at depth, their tissues converted into energy that supports the whale's long migrations and social life. For the squid population as a whole, this predation pressure is significant. Sperm whales are among the primary natural regulators of large squid numbers in deep pelagic ecosystems. Their hunting activity shapes squid distribution, influences behavior, and contributes to evolutionary selection for improved sensory awareness, propulsion efficiency, and defensive capability. Not all squid are taken. Many evade detection. Others escape during pursuit. Some survive initial contact. These survivors carry scars of their own, damaged arms, healed mantle abrasions, subtle asymmetries in movement. Each mark represents a near-fatal encounter that refined future responses. Over evolutionary time, this predator-prey relationship has driven specialization on both sides. Whales have developed powerful echolocation and extreme diving physiology. Squid have evolved enormous eyes, rapid jet propulsion, flexible bodies, and sucker-lined limbs capable of resisting massive force, even briefly. This is not a battle with a winner. It is a dynamic balance. Energy flows from squid to whale. Carbon moves from mid-water ecosystems to surface breathers. Nutrients are redistributed through digestion and excretion. The interaction links deep pelagic food webs with surface oceans, tying distant layers together through motion and metabolism. Most of these encounters pass unseen. They unfold in silence, recorded only in tissue and memory. Yet they are central to the structure of deep-sea life. They shape migration patterns. They influence growth rates. They determine which individuals reproduce and which do not. In this way, the giant squid does not exist in isolation. Its life is continuously shaped by forces larger than itself, moving through darkness with acoustic precision. And somewhere below the waves, even now, another descent begins. In the deep pelagic ocean, history is not recorded in sediment layers or coral growth rings. It is written on living bodies. For the giant squid, every scar is a compressed archive of experience, a physical record of encounters that did not end in death. As adulthood advances, marks begin to accumulate. Some are small abrasions along the arms, left behind by struggling prey or brief contact with gelatinous predators. Others appear as shallow grooves across the mantle, evidence of near misses during sudden escapes. Occasionally, deeper injuries tell of far more serious events: tentacle tips torn, suckers damaged, sections of arm partially lost. These wounds are not unusual. They are expected. Life in open water offers no shelter, and interactions occur at close range, often at speed. Yet survival depends not on avoiding injury entirely, but on healing. Cephalopods possess remarkable regenerative capacity. Damaged tissue is gradually rebuilt. Arm tips can regrow. Sucker rows reorganize. Muscle fibers reconnect. Over weeks to months, function returns, though subtle asymmetries often remain. These imperfections alter movement slightly, reshaping hunting posture and escape angles in ways that persist for the rest of the animal's life. Healing is metabolically expensive. Following injury, circulation increases to affected areas. Nutrients are redirected toward tissue repair. During these periods, feeding may intensify if prey is available, or activity may decrease to conserve energy. The squid becomes more cautious, relying on camouflage and reduced movement while regeneration proceeds. Each recovery reshapes behavior. A squid that has lost part of a tentacle learns new strike distances. One that has suffered mantle damage adjusts propulsion patterns. An individual that has narrowly escaped a large predator becomes more sensitive to distant pressure changes and acoustic disturbances. Experience is translated directly into physiology. There is no memory stored in stories or shared with others. There is only muscle memory, only altered reflexes, only scars. Over time, these cumulative changes produce individuals that are behaviorally distinct. Some become more conservative hunters, striking only when alignment is nearly perfect. Others rely more heavily on rapid propulsion, preferring to reposition frequently rather than wait passively. The deep sea selects not for uniformity, but for strategies that work under specific conditions. Scars also reveal the scale of interactions occurring beyond human observation. Circular sucker impressions on whale skin tell one side of the story. Linear abrasions on squid arms tell the other. Together, they form a distributed archive of predator-prey encounters spread across thousands of square kilometers and hundreds of meters of depth. Not every injury comes from whales. Competitive interactions with other large cephalopods may leave marks. Collisions with fast-moving fish can cause localized damage. Even turbulent water generated by passing animals can twist arms or strain mantle tissue. The open ocean is not empty. It is crowded with motion. Internally, recovery is coordinated by a nervous system that integrates pain response, movement adjustment, and tissue repair. Sensory input from damaged areas alters posture immediately, reducing strain on injured regions. As healing progresses, normal movement patterns gradually return, though rarely in exactly the same form. The squid does not become weaker through these encounters. It becomes refined. Each survival event compresses uncertainty into adaptation. Reaction times change. Escape thresholds adjust. Hunting strategies evolve. Over years, the animal becomes a living summary of its own history, shaped continuously by what it has endured. There is no point at which this process stops. Even in later adulthood, new scars appear while old ones fade. The body remains in constant negotiation with its environment, balancing injury and repair, risk and restraint. In this way, survival is not a single achievement. It is a repeated outcome, a series of narrow margins, a succession of moments where timing, perception, and movement align just well enough. And so the giant squid carries its past forward on its skin, each healed wound a testament to persistence in a world where every interaction may be decisive. Intelligence in the deep sea does not express itself through social bonds. It does not rely on shared learning, and it is rarely displayed through play or vocalization. For the giant squid, cognition emerges in solitude, shaped by the demands of darkness, distance, and constant uncertainty. At the center of this system lies a uniquely organized brain. Unlike vertebrates, whose brains sit neatly protected within a skull, the squid's central nervous mass forms a ring around the esophagus. Food passes directly through this neural loop on its way to digestion. This arrangement reflects a body plan evolved for efficiency, where sensory processing, motor control, and feeding are physically intertwined. But intelligence in the squid is not confined to this central structure. Much of its neural processing is distributed. Each arm contains its own dense network of neurons, capable of local decision-making. Suckers respond independently to tactile input. Arms can adjust grip strength and positioning without waiting for commands from the central brain. This decentralized architecture allows rapid reactions during hunting and defense, reducing delays in a world where milliseconds matter. Information flows continuously from multiple sources. The eyes deliver visual contrast and motion data. Pressure-sensitive tissues detect nearby movement. Staticists provide orientation in three-dimensional space. Chemical receptors sample the surrounding water for biological cues. All of these inputs converge in coordinated patterns that guide posture, propulsion, and tentacle deployment. The squid does not think in the human sense. It integrates. Sensory signals are translated directly into action through tightly coupled neural pathways. There is no separation between perception and response. A detected shadow becomes a change in mantle tension. A pressure disturbance becomes an altered fin angle. A moving silhouette becomes an extending tentacle. Learning occurs through repetition. Each successful hunt strengthens specific neural connections. Each failed strike adjusts timing. Each escape from danger recalibrates thresholds for movement and stillness. Over years, these accumulated adjustments produce behavior that appears deliberate, even strategic. Yet it arises entirely from experience encoded in nerve and muscle. Memory here is embodied. It lives in reaction speeds, in preferred strike distances, in the subtle way fins stabilize after injury. There are no shared traditions, no imitation, no transfer of knowledge between individuals. Every squid builds its own internal model of the deep, shaped solely by personal encounters. This isolation has consequences. It produces animals that are behaviorally unique. Some become conservative, waiting longer before attacking. Others become more mobile, repositioning frequently to sample larger volumes of water. Both strategies can succeed, depending on local conditions. The nervous system supports this flexibility, allowing continuous adjustment without external reference. Internally, coordination is maintained by massive nerve fibers, some of the largest in the animal kingdom, which transmit signals rapidly to mantle muscles during jet propulsion. These giant axons enable explosive escapes and precise thrust control, ensuring that movement remains synchronized across the body even under extreme stress. At the same time, slower pathways manage background processes, digestion, circulation, chromatophore modulation, and gradual fin adjustments. Together, fast and slow systems create a layered control architecture suited to alternating stillness and sudden action. This neurological design reflects the squid's ecological niche. It does not require long-term planning. It does not navigate fixed territories. It does not engage in social negotiation. Instead, it must constantly interpret a shifting field of light, pressure, and motion, responding instantly to opportunities and threats while conserving energy over long intervals. The result is a form of intelligence optimized for immediacy, awareness without reflection, decision without deliberation, adaptation without instruction. In this way, the giant squid represents a different pathway of cognitive evolution, one that favors distributed processing, rapid sensory motor coupling, and individual experience over collective learning. Here, in layered darkness far from surface minds, intelligence becomes quiet and functional, expressed not through communication, but through timing, through restraint, through perfectly placed movement in a world that never stops changing. Movement in the deep ocean is rarely linear. It is layered, vertical, and shaped by forces far larger than any single animal. For the giant squid, migration does not follow coastlines or landmarks. Instead, it unfolds through columns of water, guided by temperature gradients, prey availability, and the slow architecture of global currents. Unlike surface animals that migrate across visible landscapes, the squid migrates through depth. Its world is stacked in invisible floors. Each layer carries its own temperature, oxygen concentration, and biological community. Seasonal changes at the surface, phytoplankton blooms, shifting winds, altered current strength, cascade downward over weeks and months, reshaping prey distribution far below. The squid responds to these changes gradually. There is no single departure point, no clear arrival, only continuous adjustment. During periods of increased surface productivity, more organic material sinks into deeper waters. Zooplankton populations expand. Midwater fishes become more abundant. These changes ripple through the food web, drawing predators upward into slightly shallower layers where feeding efficiency improves. The squid follows, not abruptly, but through slow ascents measured in tens of meters per day, rising just enough to intersect denser prey fields while remaining below zones of intense surface light. In colder seasons, or when productivity declines, prey becomes scarce in upper twilight layers. The squid then shifts deeper, returning to darker, more stable regions where metabolism slows and energy expenditure can be minimized. These vertical migrations are subtle but persistent. Over months, an individual may oscillate across several hundred meters of depth, tracking the moving balance between opportunity and conservation. Horizontally, a different process unfolds. Deep ocean currents carry the squid across vast distances without active navigation. These currents operate on planetary scales, linking basins and redistributing heat, nutrients, and life. The squid becomes part of this circulation, drifting along invisible highways while maintaining local control over depth. In this way, seasonal movement is both passive and active. Currents transport the squid laterally. Physiology governs its vertical position. Together, these processes shape a wandering existence that can span hundreds or even thousands of kilometers over a lifetime. There are no fixed migratory routes. Each individual follows a unique path, determined by where it hatches, which currents it encounters, and how regional productivity evolves during its years of growth. Two squid born in similar locations may end up inhabiting entirely different parts of an ocean basin. This variability is not random. It reflects the dynamic structure of the pelagic environment. Temperature fronts shift. Oxygen minimum zones expand and contract. Prey layers thicken or disperse. The squid continuously samples these conditions through sensory input and metabolic feedback, adjusting depth and activity accordingly. During favorable periods, feeding increases. Growth accelerates. Arms thicken. Mantle muscles strengthen. During leaner intervals, the squid reduces movement, relying on stored reserves while drifting quietly in deeper layers where conditions are more stable. These long-term migrations also influence reproductive timing. As individuals approach maturity, they may shift toward regions where conditions favor spawning success, areas with suitable temperature ranges and current patterns that will disperse eggs effectively through the water column. Again, there is no congregation, no gathering of adults. Spawning occurs in isolation, embedded within the same drifting system that carried the squid throughout its life. Seasonal migration, then, is not a journey between places. It is a continuous negotiation with a moving environment. A slow choreography between physiology and physics. A balance between feeding opportunity and energetic restraint. Through this process, the giant squid becomes both traveler and passenger, actively choosing depth while surrendering distance to the ocean itself. Above, seasons are marked by changing skies and temperatures. Below, they are expressed through gradients of food, oxygen, and pressure. And within these gradients, the squid moves quietly, year after year, tracing invisible paths through vertical seas. In the open ocean, food does not arrive on schedule. It comes in pulses, in waves of abundance followed by long intervals of scarcity. For the giant squid, survival depends on the ability to move fluidly between these extremes. There are nights when prey layers thicken dramatically. Small fishes gather in dense schools. Mid-water crustaceans swarm upward with the darkening surface light. Bioluminescent activity increases, tracing moving bodies in faint halos of glow. On these occasions, the squid encounters opportunity. It positions itself beneath drifting aggregations, hovering with minimal fin movement, allowing silhouettes to pass overhead. Feeding tentacles deploy repeatedly, arms close. The beak works steadily. One capture follows another, separated by brief pauses as the squid reorients and returns to stillness. This is not chaos. It is controlled intensity. Even during abundance, the squid does not chase wildly through prey fields. Instead, it relies on ambush positioning and precise strikes, maximizing energy intake while minimizing unnecessary motion. Each successful capture adds to internal reserves, converting scattered biomass into muscle, neural tissue, and stored energy. Circulation increases during these periods. The three hearts elevate flow rates. Oxygen delivery rises. Digestive activity accelerates. Nutrients are distributed rapidly throughout the body, supporting tissue maintenance and continued growth. Arms thicken incrementally. Mantle fibers strengthen. Small injuries incurred during hunting begin to repair. These feeding windows may last hours, sometimes longer, but they do not persist. Eventually, prey disperses. Vertical migrations reverse, currents shift, the glowing clouds fade, and the squid returns to quiet. What follows are the long fasts. Days, sometimes weeks. During these intervals, the squid reduces activity dramatically. Jet propulsion becomes rare. Fin movements slow. The body settles into extended hovering, drifting gently within deeper layers where temperature and oxygen levels remain relatively stable. Metabolic rate declines. Energy consumption drops. Stored reserves accumulated during feeding events sustain basic physiological processes. This capacity for fasting is essential. In the deep pelagic environment, predictable access to food does not exist. The squid must endure prolonged periods with little or no intake, relying on biochemical efficiency rather than constant replenishment. Internally, the transition from feeding to fasting involves coordinated regulation. Digestive processes complete. Excess nutrients are stored. Circulation returns to baseline levels. Muscle tone relaxes. Chromatophores adopt low-contrast patterns that reduce visibility while conserving neural activity. The squid becomes almost motionless. Yet awareness remains. Sensory systems continue sampling the surrounding water. Pressure changes are monitored. Faint shadows are tracked. Even in deep rest, the animal stays prepared for sudden opportunity or threat. These alternating phases, frenzy and fasting, shape the squid's entire life history. Growth occurs in pulses, driven by episodic access to prey. Maintenance dominates between those pulses. Over years, this pattern produces large individuals built not through steady intake, but through repeated cycles of acquisition and conservation. Behavior adjusts accordingly. During feeding-rich periods, the squid may occupy slightly shallower layers where prey density is higher. During lean times, it retreats deeper, trading opportunity for stability. This flexibility allows it to persist across changing ocean conditions, responding dynamically to fluctuations in productivity that originate far above. Not every feeding event is successful. Some nights yield little. Some prey escape. Some layers prove unexpectedly empty. These failures reinforce restraint. The squid learns not to expend energy chasing diminishing returns. Patience becomes as important as precision. Through this metabolic rhythm, the giant squid integrates itself into the broader oceanic system. Surface productivity fuels plankton. Plankton supports fish. Fish sustains squid. Squid biomass, in turn, supports larger predators and ultimately returns nutrients to deeper waters through waste and eventual decay. Energy flows vertically through the water column, mediated by countless feeding and fasting cycles unfolding in darkness. Here, abundance is temporary, scarcity is common, and survival belongs to those that can endure both without excess. The giant squid does not depend on constant success. It depends on balance. on knowing when to strike and when to wait, on converting brief moments of plenty into long stretches of persistence. From the surface, storms appear loud and immediate, wind tears across waves, rain strikes water in countless impacts, cloud systems spiral across satellite images. But far below, where the giant squid lives, there is no thunder, no crashing surf, no visible sky. And yet, the deep ocean feels everything, not as sound or light, but as change. Surface storms inject energy into the upper layers of the sea. Strong winds mix warm and cold water, reshaping temperature gradients that normally remain stable. Powerful weather systems deepen surface mixing, pulling nutrients upward from below and redistributing plankton across wide regions. These effects do not stop near the surface. They travel downward. Internal waves propagate through the water column like slow-moving tides within tides, carrying the signature of distant storms into mesopelagic and bathypelagic layers. Density boundaries shift. Oxygen concentrations fluctuate. Prey distributions rearrange themselves quietly, days or weeks after clouds have already moved on. For the squid, these changes arrive without warning. There is no visual cue, only altered gradients. Only subtle differences in water density felt through the body. Only shifts in bioluminescent activity as plankton communities respond to new conditions. The squid adapts through sensitivity. Pressure-detecting tissues register internal wave passage as gentle oscillations. Staticists note changes in buoyancy. The animal adjusts fin angles and mantle tension to remain neutrally suspended as surrounding layers rise and fall. These are not dramatic responses. They are continuous corrections. Storm-driven mixing at the surface often increases productivity in upper waters. Phytoplankton blooms may follow, supporting expanded zooplankton populations. Weeks later, this cascade reaches deeper levels as increased organic material sinks through the column. Marine snow becomes denser. Small prey species grow more abundant. Mid-water fish redistribute. Eventually, these shifts intersect with the squid's feeding range. On such occasions, the squid experiences improved hunting conditions. Prey layers thicken. Feeding becomes more frequent. Growth accelerates slightly. The effects of a distant storm may thus be recorded not in memory, but in muscle mass, in repaired tissue, in strengthened arms. Other times, storms disrupt prey aggregation. Currents scatter schools. Oxygen-poor layers expand or contract unpredictably. Food becomes harder to locate. In response, the squid retreats deeper, reducing activity and relying on stored reserves until conditions stabilize. Climate variability adds another layer. Seasonal wind patterns, large-scale oscillations, and shifting ocean circulation influence long-term productivity across entire basins. These processes determine where prey will be abundant months later and which regions will become comparatively sparse. The squid does not perceive climate. It experiences consequences. Altered temperature profiles change metabolic demands. Shifting oxygen levels influence preferred depth. Modified current strength alters horizontal transport. Each of these factors feeds back into daily behavior and seasonal movement. Even seismic events and distant storms can generate pressure waves that propagate through deep water. These are usually subtle, but to a creature tuned to fluid motion, they register as temporary disturbances, brief deviations from the background quiet. Yet despite all this connectivity, the deep remains remarkably calm. After surface turbulence fades, the midwater returns to slow drift. Internal waves dissipate, particle flux stabilizes. The squid resumes its familiar rhythm of hovering, hunting, and conserving energy. From a human perspective, storms feel episodic. For the squid, they are part of a continuous environmental spectrum, folded into the larger pattern of gradients that define its world. Nothing arrives as an isolated event. Everything becomes a gradual shift. In this way, the giant squid lives in a planet-wide system of delayed cause and effect, where distant winds reshape feeding opportunities, where surface productivity determines deep survival, and where silence below carries the echo of weather far above. For most of its life, the giant squid exists entirely alone. There are no companions during migrations, no shared hunting grounds, no social structure carried from youth into adulthood. Yet for reproduction to occur, two solitary trajectories must briefly intersect within a vast and moving ocean. These encounters are rare. They are not announced. They are not synchronized by seasons in any strict sense. Instead, they emerge from overlapping movement patterns, individuals drifting through similar depth ranges as they approach reproductive maturity, guided by the same gradients of temperature, prey availability, and current flow. There is no gathering place, no breeding ground. Courtship in the deep pelagic environment is defined by chance alignment. When two adults come within proximity, detection occurs first through subtle disturbance in surrounding water. Pressure-sensitive tissues register nearby motion. Visual systems pick up faint silhouettes against background darkness. Bioluminescent plankton may briefly outline approaching forms, offering momentary confirmation of another large body moving through the same layer. The squid does not call out. There are no vocal signals, no long-distance communication. Recognition is immediate and local. At close range, posture changes. Arms adjust orientation. Chromatophores shift brightness slightly, producing low contrast patterns that reflect internal physiological state. These changes are not elaborate displays. They are brief, functional cues, subtle variations in tone and tension that accompany heightened neural activity. Physical proximity replaces visual ceremony. The two animals orient toward one another, their long arms extending cautiously. Contact occurs through gentle touches of suckers along mantle and limbs, confirming species identity and readiness. This tactile exchange replaces the complex visual rituals seen in shallow water cephalopods. Mating itself is brief. The male transfers spermatophores, packets of sperm, directly to the female using a specialized arm or direct placement along receptive tissue. This process may leave small marks or abrasions, additional entries in the ongoing record written on the body. There is no prolonged pairing, no guarding behavior, no continued association afterward. Once transfer is complete, the individuals separate, each returning to solitary movement through the water column. Fertilization occurs internally. The female later releases fertilized eggs into open water, allowing currents to disperse them across wide regions. There is no parental investment beyond this moment. Survival of offspring depends entirely on probability and environmental conditions. This reproductive strategy reflects the realities of the deep pelagic world: low population density, vast distances, unpredictable encounters. Evolution has favored brief, efficient mating events rather than extended courtship or pair bonding. After reproduction, physiological changes begin. Energy reserves decline. Tissue repair slows. Activity levels gradually decrease. For many individuals, spawning marks the final major phase of life. The body, having invested heavily in reproduction, enters a period of progressive weakening. But even here, there is no abrupt end. The squid continues drifting, continues feeding when possible, continues responding to gradients and disturbances. Life does not conclude with ceremony. It simply transitions. Courtship in black water is not romantic. It is functional. A fleeting convergence of two independent lives within an enormous, indifferent environment. A brief exchange that ensures continuity across generations. And then separation, two paths diverging once more into layered darkness. Reproduction in the open ocean leaves no monuments, no nests, no guarded territories. For the giant squid, passing life forward is an act carried out entirely within moving water, entrusted to currents that circle the planet. After mating, the female continues her solitary existence, drifting through familiar layers of depth while internal processes unfold. Spermatophores received during brief encounters release sperm gradually, allowing fertilization to occur over time. Energy that once supported growth and hunting is redirected toward egg production. Thousands of developing ova accumulate within the body. Each one is small, nearly transparent, yet complete in potential. This investment is immense. Producing eggs requires large amounts of protein and lipid reserves, drawn from tissues built over years of feeding and fasting. As this allocation progresses, the female's overall condition begins to change. Muscle tone softens slightly. Activity levels decline. Feeding becomes less frequent, not because prey disappears, but because internal priorities shift. When release finally occurs, it is not synchronized with any visible signal. There is no surface cue, no seasonal marker that humans could recognize. Spawning happens when physiology and environment align, when temperature ranges, depth conditions, and current structure favor broad dispersal. The eggs are released directly into open water, not as a single mass placed carefully in one location, but as diffuse clouds suspended in the pelagic column. These gelatinous aggregations drift immediately, stretching and thinning as surrounding currents pull them apart. Within minutes, individual eggs begin to separate, each becoming an independent traveler. From this moment forward, there is no connection between parent and offspring. The ocean becomes nursery, currents become carriers, probability becomes protection. Most eggs will never hatch. Some will be consumed by plankton feeders within hours. Others will fail during early development. This high mortality is not a flaw in the system, it is its foundation. The strategy relies on abundance rather than care, on numbers rather than shelter. For the small fraction that survive, embryonic development proceeds slowly in cold, pressurized water. Cells divide, primitive organs form, tiny hearts begin their first contractions. Neural pathways start assembling long before any movement occurs. All of this unfolds unseen. Weeks later, fragile larvae emerge. They are almost invisible. Their bodies scatter light. Their arms are short. Their propulsion weak. They drift upward into slightly brighter layers, entering the planktonic world where their earliest feeding and growth will take place. This marks the beginning of another generation's journey. For the parent, however, reproduction marks a turning point. Energy reserves are depleted, tissue repair slows, responsiveness diminishes. The body that once hunted efficiently now enters gradual decline. There is no immediate collapse. The squid continues drifting. It may still feed occasionally. It still responds to pressure changes and shadows, but strength fades. Mantle contractions weaken. Jet propulsion becomes less frequent. Over time, the animal sinks into deeper layers where activity drops further and metabolic demands decrease. Eventually, death arrives quietly. There is no dramatic final moment. The body simply ceases coordinated movement. It begins its slow descent toward the seafloor, becoming part of a different ecosystem, one that depends on falling organic matter for survival. Scavengers gather. Microorganisms proliferate. Stored carbon is redistributed. Nutrients re-enter circulation through deep currents. In this way, reproduction does not end with offspring alone. It also returns accumulated energy back to the ocean interior. Life continues in two directions at once. Upward through drifting eggs and rising larvae, downward through sinking biomass and benthic communities. This dual flow links generations across depth, ensuring that the squid's existence shapes ecosystems both above and below its primary habitat. Passing life forward is not a single event. It is a transfer of material, energy, and probability across moving water. A quiet exchange that sustains continuity in one of Earth's most inaccessible environments. Aging in the deep ocean is not marked by wrinkles or graying skin. It is measured in slowing responses, in softer muscle tone, in the gradual shortening of endurance for the giant squid. This phase begins quietly, long after reproduction has redirected internal resources and long before movement finally ceases. There is no clear boundary between maturity and decline. Instead, small changes accumulate. Jet propulsion becomes less frequent. Fin movements grow gentler. The mantle no longer contracts with the same power it once held. These are subtle shifts, barely noticeable from one day to the next, yet over weeks and months they reshape how the animal occupies its layered world. Energy allocation changes. What once fueled growth and rapid recovery now supports only maintenance. Tissue repair slows. Minor injuries linger longer before healing. The circulatory system continues its steady work, but peak performance fades as muscle fibers lose elasticity and neural signaling becomes slightly less efficient. Hunting still occurs. The squid remains capable of capturing prey when opportunity presents itself, but it becomes more selective. Long pursuits are avoided. Ambush positioning replaces active repositioning. The animal waits longer between strikes, conserving energy by extending periods of stillness. Metabolic rate declines. In colder, deeper layers, this reduction offers stability. Here, temperature is nearly constant. Oxygen levels are low but predictable. The squid settles into these depths more often, trading access to dense prey fields for an environment that demands less physiological output. Vertical migrations short. Nightly ascents become smaller in amplitude. Eventually, some individuals cease regular migration altogether, remaining in deeper zones where pressure is high and movement can be minimized. Internally, reserves accumulated over years are slowly drawn down. Lipids stored in tissues provide fuel during extended fasting. Protein turnover continues at a reduced pace. The balance between intake and expenditure narrows, leaving little margin for unexpected stress. Sensory systems remain active. The eyes still track faint motion. Pressure-sensitive tissues continue to register passing disturbances, but reaction times lengthen. Escape thresholds rise. Where once a distant vibration would trigger immediate propulsion, now the squid often waits until a stimulus is closer, conserving strength for moments that truly require it. The body carries the record of its life. Healed scars remain visible. Arms may show asymmetry from earlier injuries. Suckers vary in size where regeneration was incomplete. These imperfections subtly alter movement patterns, reinforcing cautious behavior. Experience, once translated into refined hunting and escape strategies, now becomes restraint. There is no withdrawal from the environment. The squid continues drifting within the same dynamic gradients of temperature and density. Currents still transport it laterally across unseen distances. Marine snow still falls past its body in slow, continuous streams, but participation becomes quieter, activity narrows, presence becomes more passive. Eventually, coordination weakens. Mantle contractions lose synchronization. Fin adjustments lag behind changes in buoyancy. The animal spends longer intervals in near motionless suspension, responding only to the strongest stimuli. Death does not arrive as a dramatic event. It emerges from gradual physiological exhaustion. Circulation slows, neural signals fade, muscle tone collapses. The squid simply stops maintaining its position in the water column. Gravity takes over. The body begins its final descent. What follows is not disappearance but transformation. As the squid sinks, it enters a different ecological network. Scavengers detect the falling biomass. Microorganisms begin breaking down tissue. Stored carbon and nutrients are released into deeper layers, fueling communities that depend entirely on material drifting down from above. The individual life ends, but its substance continues moving through the ocean system. Aging in cold pressure is not a retreat from existence. It is a transition from active participation to redistribution, from hunter to habitat, from moving body to sinking resource. Here in the deep, endings are not abrupt. They are absorbed into circulation. As the end of life approaches, movement becomes quieter, not faster, not farther, but more deliberate. For the giant squid, there is no mapped destination called a spawning ground. No reef, no basin, no fixed coordinate in the ocean. Instead, the final journey unfolds through gradients, shifts in temperature, subtle changes in oxygen, and current structures that favor the dispersal of eggs. This is not migration in the traditional sense. It is alignment. Physiology begins to guide depth preference more strongly than feeding opportunity. Individuals approaching reproduction tend to settle into layers where thermal stability is high and currents move predictably. These conditions increase the likelihood that released eggs will be carried broadly through the pelagic system, rather than concentrated in one place. The squid does not travel with urgency. Jet propulsion is used sparingly. Fins maintain slow, stabilizing motion. Most movement occurs through passive drift, allowing large-scale circulation to determine horizontal position, while the animal maintains control over depth. Over weeks, sometimes months, this process shifts the squid gradually into regions that support successful spawning. Feeding becomes secondary. Energy intake declines as internal reserves are redirected toward reproductive tissues. The mantle still contracts when necessary, but bursts of speed are rare. Hunting, when it occurs, is conservative. Targets are chosen carefully, and long pursuits are avoided. Internally, reproductive development continues. In females, eggs mature in large numbers. In males, spermatophores are prepared for transfer. These changes reshape body composition and alter buoyancy slightly, requiring continuous adjustment through fin angle and mantle tension. The squid compensates automatically, maintaining neutral suspension despite changing internal mass. Encounters with others remain uncommon. Population density in deep pelagic environments is low, and individuals are distributed across vast volumes of water. When two mature adults do intersect, it is typically the result of shared responses to the same environmental gradients rather than intentional convergence. These meetings are brief. After mating, separation follows almost immediately. Each individual resumes its solitary drift. Following reproduction, the final journey continues downward. Activity levels decrease further. Vertical migrations shorten or cease. The squid spends increasing amounts of time in deeper, colder layers where metabolic demands are reduced and external disturbances are minimal. Here, light is nearly absent. Bioluminescent flashes become rare. The environment settles into near constant darkness. This descent is gradual. There is no sudden plunge, just a slow surrender to depth as strength wanes and buoyancy regulation becomes less precise. Throughout this period, the squid remains responsive to its surroundings. Pressure changes are still detected. Shadows are still registered, but reaction thresholds rise. What once triggered immediate propulsion now prompts only minor adjustment. Energy is conserved for essential physiological processes. The body prioritizes internal balance over external engagement. From a broader ecological perspective, this final movement serves multiple functions. It places spawning adults within current regimes that maximize egg dispersal. It shifts aging individuals away from densely populated feeding layers, reducing competition with younger squid. And it positions declining bodies closer to deep communities that will ultimately recycle their biomass. The journey is both personal and systemic. It completes an individual life cycle while reinforcing nutrient pathways that sustain the larger ocean. There is no ceremony, no gathering, no visible endpoint. Just a solitary animal drifting through layered water, guided by chemistry and current, moving steadily toward redistribution. Here, in the deep pelagic realm, the final journey is not about arrival. It is about transition. From active predator to drifting parent, from drifting parent to sinking resource, from living structure to circulating matter in the deep pelagic world. Endings do not arrive as silence, they arrive as transfer. When the giant squid finally loses the ability to maintain buoyancy, the body begins its slow descent through layered water. There is no sudden collapse. Coordination simply fades. Mantle contractions cease. Fins stop correcting position. Gravity, long held at bay by muscle and chemistry, reasserts itself. The squid starts to sink. At first, the descent is gentle. Cold water slides past arms that once reached outward in decisive strikes. Chromatophores remain fixed in their last low-contrast state. The eyes, once tuned to faint motion, now reflect only darkness. The body rotates slightly as it falls, passing through temperature gradients and pressure boundaries that shaped its entire life. This is not disappearance, it is relocation. As the carcass moves downward, it becomes a traveling resource, an island of concentrated energy entering ecosystems that survive almost entirely on material raining from above. Chemical signals disperse into surrounding water. Scavengers detect them quickly. Amphipods, hagfish, deep-sea fishes, and countless microorganisms begin converging from surrounding darkness. Some arrive within hours, others follow over days. The falling squid becomes a beacon in an environment where large meals are rare. The first arrivals feed on exposed soft tissue. Arms and mantle are opened. Muscle fibers are stripped away. What took years to build is redistributed in days. As decomposition progresses, microbial communities bloom across remaining surfaces. Bacteria break down complex proteins and lipids, releasing nutrients back into the water column and sediments. These microbes, in turn, support higher trophic levels, tiny grazers, then larger predators, forming a temporary but intense food web centered on a single body. This process mirrors what occurs when whales die and sink, though on a smaller scale. The principle is the same. Large pelagic animals act as vertical conveyors of carbon and nutrients, transporting energy from productive surface waters to the deep sea. In death, the squid completes this role, delivering concentrated organic matter to communities that would otherwise rely only on sparse marine snow. Over time, little remains. Soft tissues vanish first. Cartilaginous structures persist longer. Eventually, even these are dismantled, incorporated into sediments, or carried away by currents. What was once a powerful hunter becomes dispersed molecules, carbon dioxide, nitrogen compounds, dissolved organic matter, re-entering circulation pathways that span entire ocean basins. This is not waste. It is recycling on a planetary scale. The squid's final contribution supports scavengers, fuels microbial respiration, and enriches deep water chemistry. That chemistry influences productivity elsewhere, feeding currents that eventually rise toward the surface, closing loops that link abyssal plains to sunlit seas. From an ecological perspective, death is not an endpoint. It is a redistribution event, a pulse of energy moving downward through the water column, a reinforcement of connections between distant layers. For every giant squid that sinks, countless smaller organisms benefit, directly through feeding, indirectly through nutrient release, and ultimately through altered chemical gradients that shape future productivity. In this way, the animal continues participating in ocean systems long after coordinated movement has stopped. Its life supported predators. Its death supports decomposers. Both phases are essential. Here, in the deep, individual existence dissolves into collective process. Nothing truly disappears. Everything transforms. In the end, there is no monument, no reef to mark a lifetime, no surface trace that remains for the giant squid. Legacy is not carved into stone or coral. It is written into circulation, into currents, nutrients, and probability, distributed across an ocean that never truly rests. What begins as drifting eggs becomes drifting larvae. What grows into a solitary hunter becomes sinking biomass. And what sinks is transformed again into chemistry that feeds future life. This is the quiet continuity of the deep. Across generations, the giant squid persists not through visibility, but through repetition. Each individual follows a similar arc: emergence in open water, growth through alternating abundance and scarcity, brief convergence for reproduction, gradual decline, and eventual redistribution into the ecosystem. No single life defines the species. The pattern does. From a systems perspective, the squid functions as both consumer and conveyor. During life, it concentrates scattered energy by converting midwater prey into structured tissue. In death, it delivers that accumulated carbon to deeper layers, supporting scavengers and microbial communities. Over geological time, countless such transfers help regulate nutrient balance between surface productivity and abyssal storage. Its role is subtle but significant. It links trophic levels that rarely meet directly. It bridges pelagic and benthic worlds. It participates in the ocean's biological pump, moving material downward through bodies rather than particles alone. Even its predators extend this influence. When whales consume squid and later release waste near the surface, nutrients are lifted back towards sunlit waters. When squid sink intact, they feed the depths. Together, these pathways create loops that circulate matter vertically across kilometers of water. The squid's existence is therefore not isolated. It is embedded within planetary flow. Yet, despite this importance, the animal remains largely unseen. Most giant squids live and die without ever entering human awareness. Our knowledge comes from fragments, rare encounters, stranded individuals, brief camera footage, scars on whales, and biochemical traces in deep sediments. These pieces form a partial picture of a creature that occupies one of Earth's largest habitats. What science has revealed so far is not a monster. It is an organism exquisitely tuned to scarcity, pressure, and darkness. A body built for waiting. A nervous system optimized for immediate response. Eyes designed to read faint gradients rather than bright scenes. Movement shaped by restraint as much as speed. Its intelligence is not social. Its communication is not vocal. Its world is not structured by landmarks. Instead, it navigates through gradients, light fading to black, temperature slipping toward cold, oxygen thinning with depth, making continuous adjustments that allow persistence in an environment defined by change. In this sense, the giant squid represents a broader truth about deep-sea life. Survival here does not depend on dominance. It depends on efficiency, on flexibility, on the ability to convert brief opportunity into long-term endurance. Every generation repeats this experiment. Some larvae survive. Some juveniles grow, some adults reproduce. Most bodies return to circulation. The lineage continues not because individuals prevail, but because the system allows replacement. Above, continents shift slowly. Climate patterns rise and fall. Human history advances in short, crowded chapters. Below, the deep ocean maintains its own pace, measured in currents, nutrient flux, and the quiet persistence of organisms adapted to absence. Here, the giant squid remains an eternal drifter, not fixed in place, not bound to territory, moving through layered water generation after generation, leaving no trail but influence. Its legacy is not spectacle, it is continuity, a presence felt through chemistry rather than sight, a life expressed through transfer rather than permanence. And so, far beneath storms and sunlight, beyond familiar horizons, the story goes on. Eggs disperse, larvae rise, hunters form, bodies sink. Nutrients circulate in this endless exchange. The giant squid endures not as an icon of mystery, but as a working component of Earth's largest living system, drifting, transforming, returning, again and again.